Our last topic in polynomials is talking about polynomial functions and their end behavior. Now, I know we've talked about end behavior before in Algebra 2, but I know, again, that's been a minute, at least a summer, maybe a year and a half for some of you. So let's just, without a lot of hoopla in how we're writing it at first, let's just talk about what end behavior is. End behavior of a function describes how the function behaves as it moves infinitely to the right and to the left. It is literally what's happening at the end of the picture that you're looking at. In other words, the end behavior is what happens to the values of the function f of x, the outputs, as x increases without bound. So, x increasing without bound means that we're looking for where x approaches positive infinity. That's what those symbols are going to mean today. The arrow is the word approaches. Good morning. X approaches infinity, or we're going to look and see what is happening to x as x decreases without bound, which means that those x values are going to negative infinity. That's what we're looking at today. Really, really fancy. What that means is we are deciding what is happening to the outputs of the function as we go to the right side of the graph and as we travel backwards to the left side of the graph. And I'm going to be using the words right and left to talk about x is approaching infinity and x is approaching negative infinity. But I'm literally just talking about your x-axis going to the right or to the left. Now, in Algebra 2, I don't remember exactly what notation you use, but I do know I'm going to change to the notation you use to talk about end behavior. But without being real fancy, if we drew this graph right here, and we just kind of wrote down what was happening on the left and the right side. I'm just going to use parentheses to say what's happening on the left and on the right. Would you agree with me that on the left side, the arrow is going downwards, and on the right side, the arrow is going upwards? Do you see how that end behavior is literally just describing the arrows at the end of the graph, right? We go down, then we go up, left and right. If you were to draw a quadratic, and use the same sort of arrows right here, not a super formal way of talking about it, but what would you say for end behavior on this guy? Up, up, because at both sides, on the left and the right, we're going upwards. Those arrows are going positively. What about this sort of function? It looks like this. How would you describe the end behavior for this graph? Up on the left, down on the right. Very good. And last but not least, what if we had a function like a quartic that was upside down like this? How would you describe this one? Down, down. Okay, that's a very informal way of talking about end behavior. And that's all we're doing today is discussing how these graphs behave as they approach negative infinity on the left and positive infinity on the right. But we're going to do it in a very formal math way. You've never probably seen this sort of notation before. In Algebra 2, I think you got close to what's called a limit notation, but we're going to be writing limit statements for our end behavior in this class. So when I'm talking about the left side end behavior, which is where the values of x decrease without bound, we're writing a statement that talks about the outputs. The way you say this is you say the limit as x approaches negative infinity of f of x is, and then you give me some number. So again, that whole thing, and yes, you stack it. I think in Algebra 2, your textbook in this school didn't stack the limit statement, put it next to each other. No more, you have to stack the limit statement. This is the limit as x approaches negative infinity of f of x is whatever this number is. Okay, let's just say you can read it out. I put the words right here. Let's say it out loud. So say it along with me. 3, 2, 1. The limit as x approaches negative infinity of f of x is blah, blah, blah. Okay, great. That's how we're going to talk about end behavior here. Now, up above this, all we did was write arrows. We said it went down, then up. All this limit statement does is it describes the left side as x approaches negative infinity. So for this graph, we'd say the limit of f of x as x approaches infinity of f of x is negative infinity because it's going down. For this one, we'd say the left side end behavior is positive infinity because it's going up. But we do that for both sides. So on the right side end behavior, we're talking about when the x values increase without bound, meaning we're talking about where x approaches positive infinity this time. So the limit as x approaches positive infinity for f of x is blah, 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 whatever the limit is. In my class, I want us to be able to not only write the limit statement, but I also want us to be able to understand in verbal words what that means. So we are going to be writing a little bit today on the front of these notes to see the response that I'm looking for. But the limit statements themselves are really pretty simple, especially when we have a graph. So on this graph, let's look at the right side and on the left side. I'm going to keep coloring my graph, the left side end behavior in red and the right side in green, just because that's how I've highlighted already. But pretty simply, if this was a graph before you knew limit statements, you would have told me that this goes up, down. Yes? Cool. The limit statements are literally just a fancy way of talking about that. For the left side end behavior, we would say the limit as x approaches negative infinity for the function, this one's named g of x, is equal to positive infinity. Again, this x approaching negative infinity tells me I'm looking at the left side of the graph, and the infinity sign right here is telling me that that graph is going up on that side, because that arrow is going up, and those output values would continue to go up if we walked backwards to the left on this graph. The right side end behavior statement would be that the limit as x approaches positive infinity for the function named g of x is this time equal to negative infinity. So again, this part right here tells me that I'm talking about the right side of the graph, and this number tells me that it's going down. The outputs are going down. Do we see that? So a second ago up here when we were being super informal, we just said up, down, right? Up, up. Up is going to be positive infinity. Down is going to be negative infinity. And so on this one, since it went up, down, my left side in behavior is infinity, up. My right side in behavior is negative infinity, down. So same concept y'all are really good at seeing right away. We're just making it super formal with this limit statement. The verbal statement we would use to describe the end behavior on the left side is as follows. We would say, as the x values decrease without bound, the output values of g of x increase without bound. For our notes, without W/O on a test, you write the word out, especially if you're not sure if the reader understands that shorthand. Here's what we're saying. We're literally taking the limit statement and we're writing it in words. We're saying as the x values decrease, that's the x approaching negative infinity. The output values of the functions increase. That's the positive infinity that the output values are going to. This is the same statement as this, just in words. As the values of x decrease without bound, they go to negative infinity. The output values are going to increase without bound, continually, infinitely. If If we were writing the right side end behavior, that was a lot of words that alliterated, as the x values on the right side, the x values are going to increase without bound. For this function, the output values of g of x are decreasing. So again, to understand what we just wrote here, the x values increasing means x is approaching positive infinity. The x values are getting bigger and bigger and bigger and bigger and bigger and bigger. The output values, since we see that arrow going down, those output values are going to decrease, approaching negative infinity. I don't know why this comma is here. Let me get rid of it. Yeah, I don't know. I don't know what I was doing. So again, these statements are the same thing. Mathematicians like using symbols to represent long words because we didn't like writing out math in words. That's where all of mathematical symbols came from. So instead of writing all of this, mathematicians started writing stuff like this. We've created shorthand for everything. Yes?
For the test, will the top one be acceptable, or will we have to write it all out?
It will ask for either a limit statement, which is this, or a verbal statement, which is this. So I won't tell you yes or no yet. But for the most part, I'm going to be focusing on the limit statements, but the verbal statement should come right with it because the decrease is here and the increase comes from here. So they go hand in hand. Can I have you guys try this next one? So I want you to both write the limit statement and the verbal statement for the graph of h of x. Give it a shot. All right, on the h of x graph, let's just first look at the graph. What's happening on the left side of the graph? It's increasing. What's happening on the right side of the graph? Okay, cool. So that gives us an idea of our limit statements. They should be both going to positive infinity because those arrows are both going up. Now, writing it correctly is the point. I do need it to be completely written this way. So we would say the limit as x approaches negative infinity, that means I'm talking about the left side, of h of x, ooh, did we remember to change the letter? This function is called h, change the letter, is positive infinity. What I'm saying here is that on the left side of the graph is going up. The other limit statement would be the limit as x approaches positive infinity for h of x. Yes, you repeat everything. It's its own limit statement. But this side is also going up. So we're saying on the right side of the graph is going up. Okay, do you see the difference in these statements? Verbally, here's how we would write. Let's see if I can get it all in there. So we would say as input values, the x values decrease. I'm talking about the left side without bound, meaning they go all the way to negative infinity. They have no boundary. The output values of this function is called h of x. What do? They also increase without bound, meaning they go off to infinity and beyond. Nope, okay. So again, left side is where the x values decrease, and h of x increasing means my graph is going up on the left side. The other verbal statement I would write is as the x values this time increase without bound. That means I'm talking about the right side of the graph. The output values of the function called h of x this time, again, switch the letters. This is also going to increase without bound because they're also going up to positive infinity. Increasing without bound means I'm going to positive infinity. So x values increase is right side. Output values increase means infinity. Did we get close or did we get it? Love it. Great, awesome. Looking at a graph and talking about its end behavior is so easy because we just look at the arrows. But what if we start to take away the graphs and start to read end behaviors themselves to draw graphs? Or better yet, have no graph whatsoever? I'm so glad you asked. Let's go to the back of these notes and practice. Reading our end behaviors to sketch a function. Now remember, end behavior tells you only about end behavior. Does it tell you anything about middle behavior? That's not a thing. I just made up middle behavior. But it tells you nothing about the middle. It only tells you about the end. This function, however, these limit statements, what is happening on the left for this graph of f of x? It's decreasing. So I'm just going to prep myself with a downward facing arrow on the left because it says negative infinity. That means that arrow should be headed downwards. So numbers are getting smaller as we go to the left. What's happening on the right side of this function? Also going down. Did it tell you anything about middle behavior? No, so we could make it a cute little quadratic. I don't know what's happening in the middle. I could make it a quartic function. I could, wait for it, make it like absolutely bananas. But as long as the end behavior matches what the graph is telling you, that's all end behavior talks about, is literal end behavior. I'm going to make this look nicer though because that's a little crazy. We'll just make it a cute quadratic. So if that's the case and we start by reading end behaviors to draw the graph, what should the graph look like for these two limit statements? What's happening on the left? Decreasing without bound. What's happening on the right? Increasing without bound. A good question somebody asked me last year when I did this is, do you have to put the plus for positive infinity? No. You don't put pluses on things to show it's positive, but you can if it makes you feel better. It's not wrong. It's just unnecessary. Now again, this is all we know about this function, is that its end behavior should go down on the left and up on the right. It could be a big old linear function, a straight line. It could be a cubic function. It could be anything, any sorts of maxes and mins in between, because all I know is that on the left it has to go down and on the right it has to go up. That's the only information I have at this point. This is a cubic function. Okay. The other one was a parabola at first. Yeah. So every function we can describe the end behavior if it has an end behavior, if the arrows go a certain direction on the left and the right. And it all has to do with parts of the actual function themselves. So let's talk about polynomial end behavior. This time we're not giving you any graphs, but it's still just as easy to determine the end behavior. For polynomial equations, end behavior depends on the leading coefficient and the degree of the polynomial. So leading coefficient and the degree of the polynomial. It is easiest, by the way, to always find the right side first. I know we list them with left side first, then right side second, because smaller numbers come first. But it is actually easier to think about the right side first. When we're looking at the leading coefficient of a polynomial, if the leading coefficient is greater than 0, meaning you have a positive leading coefficient, that means that on the right side, that right side is going to go to positive infinity. Period. Leading coefficient positive means the right side goes up. A leading coefficient being negative means that the function goes to negative infinity on the right side. Notice, it's only talking about the right side. We look at the right side first. It will determine what's happening on that side. Positive goes up, negative goes down on the right side. But then we check out the degree of the function. If the degree of the function is even, so you have a power 2, power 4. If the degree of the function is even, the function goes in the same direction on the right and the left. So even numbers, they're both going to be up. They're both going to be down. If the degree is odd, the function goes in the opposite direction on the left side. So you already figured out the right side. You can just very easily move your arm for the left side. You'll see what I mean by move your arm in a second. Got ahead of myself. Here's how I remember this. Odd, opposite. Odd, opposite. Right side is controlled by the leading coefficient. The degree tells you what to do with your left hand. Do you go the same or do you go opposite? So to practice this, we're going to play a quick game. You don't have to move for this game yet. I have to switch to something else. All right, thank you so much for playing. I thought that was fun, Ms. Quigley says. But the idea of what you guys just did with your arms in that game is exactly what we're going to do when we're finding the end behavior of a polynomial when we don't have a graph. This is also why I didn't give you a calculator today. I don't want you to graph these because you don't need to, okay? We're going to determine the end behavior, and I started writing your limit statements for you so we could get through this a little faster. But every time you're talking about end behavior, you give me the whole statement. So, what is the degree of this polynomial? 5. Okay, cool. I care more that it's an odd number. But yes, it's 5. What is the leading coefficient here? 4. Now, is that greater than 0 or less than 0? Greater than 0. So we just played this game. If this were going to be your arms, if it's an odd degree polynomial with a leading coefficient greater than 0, what do your arms look like? Your right hand goes up, your left hand goes down, yeah? That means on the right side end behavior, we're going up, and on the left side end behavior, we're going down. So notice again, I'm going to write your limit statements, usually with the left one coming first because smaller numbers before bigger numbers, right? Number order. But we're going to answer this bottom one first because this one is controlled by the leading coefficient, positive, positive. This one follows with the degree, odd, opposite. You see how that works? You got the answers in your hands. We just played this whole game. What about this one? What is the degree, even or odd? Even. Is the leading coefficient greater or less than 0?
What?
Than 0? Greater. It's positive. Remember, we're just working about positive or negative, so it's greater than 0. What's happening with your arms? Yes, up, up. I see you back there. So that means that both of the limit statements go to positive infinity. So yeah, if your arms start flying around in class, I know what's happening. I get it. Okay, what about this one? What would be the degree of this polynomial? 6, which means it's an even degreed polynomial. What's the leading coefficient? Less than 0. So even and less than 0, that means that your right hand is going down and the left hand is going down. So both of the limit statements go down. Y'all see how this works? Can you try D, E, and F? Slow down on F. I will tell you that right now. D, E, and F, but slow down on F. There's a trick in that one. I want to see what you can do. Hee hee, I left you with all the hard ones. Here we go. Just to see if we've got it, what's the degree of h of x? 5. So that's an odd degree polynomial. What is the leading coefficient? -1, which means we are less than 0. The leading coefficient being less than 0 means the right side goes to -infinity, and the degree being odd means that the left side should be the opposite. Did we get that one? Did I trick you with the leading coefficient thing? Haha, you fell for my trick. What about E? Kind of same thing. What's the degree here? Odd. What's the leading coefficient? -1, which means we're less than 0. Again, less than 0 for the leading coefficient means the right side goes down. Odd, opposite, left side goes up. And then we get to F. What is the degree of F? Oh, we got to remember some things we did last class. All right. Last class we talked about zeros and their multiplicity. How many zeros would this factor have? 1. How many zeros would this factor have? How many zeros would this one have? Which means how many total zeros will I have? 3. So this is an odd degree polynomial because I have a degree 3, if that's helpful. Now, talking about the leading coefficient in this one is also kind of crazy. The leading coefficient here is not 2. If we were to multiply all of the x's together, we'd be multiplying 2x times 1x times -1x. My leading coefficient here is -2 because 2 times 1 times -1 is -2. So that means our leading coefficient here would be less than 0. And again, the right side goes down, the left side goes up. Do y'all need me to do all of that again? No. Yes, thank you for your honesty. All right, we found out the degree from the multiplicity of each of the zeros. Multiplicity 1, multiplicity 1, multiplicity 1. So degree 3, odd. The leading coefficients are what you get if it's all in factored form when you would multiply all of the x terms together. If I multiply just the x terms together, skipping the fact that, yes, you have to do double distribution. You have to do all of those things. But if I'm multiplying the x terms together, this is 2x times 1x times -1x. 2 times 1 times -1 is -2. So my leading coefficient eventually, when I multiplied all this out, would be -2x cubed. So it's odd and negative. Yes? Look quickly on the worksheet you have for today for your check your understanding. I have not written any of the limit statements on there. I gave you the limit statements on mine. Here's some things I want you to notice. Did you notice that on your notes, every single time we wrote a limit statement, it matched the output or the name of the function? So m of x, I use m of x. If it just says y, you use y. Do y'all see that? Make sure you get that part right correctly. Or what? What? Make sure you get that part done correctly. Oh my gosh. Okay, I did leave you with lefts and rights so you know to write them organized fashion, but you do need to use the correct letter there. On the back, it's all multiple choice, because this is the types of questions you might see when it comes to end behavior. The key to this is on Google Classroom already, since I didn't have room for an answer key on this document. Yes? Okay, cool.